talk about this ninth lecture series, and this one it talks about Bitcoin networks, precursors to Bitcoin, and proof of work monopoly problem. Proof of work has some problems, and then there are some alternative schemes, such as proof of X schemes, and the summary of altcoins. Okay. All right, so Bitcoin network, there are many Bitcoin networks, and there are about 3 Bitcoin networks that are doing the testing. So there are 3 test Bitcoin networks, and obviously there is a main Bitcoin network. And the purpose of having test network is for us to do some experimentations. So testnet runs the same code as the mainnet does, but one can run some experiments on them. And basically one of our network that you have done the homework could be considered as a test network for now. And one can change the protocol and run one's own Bitcoin with it. Okay, so for example, you can create your own coins, and just like what we have done in the first half of this class semester, and you can change the block generation time. You can have a different, currency issuance schedule, and then you can set up a different difficulty rules and so on. And there is a video for this lecture, so if you guys want to see more of explanation, you can take a look at them. Okay. And this is one important part. Basically, Bitcoin networks. This is a free network. I mean, you can jump in anytime you want, right? So every peer in the Bitcoin network, needs to maintain at least 8 connections, and a maximum of 125 connections. Basically, a node, when it comes to the network, listen on the same port everyone else uses. Like in the Bitcoin case is 8333, right? And then they listen on it, and if there is a request for list of neighbors, then you are supposed to give your list of neighbors to the requester, and so on. And there are many different node types, and for each node type, basically the role of the node is different, could be different. Okay, so while nodes in the Bitcoin network are equal, they may take on different roles. Okay, depending on the functionality they are supporting. Okay, and so what are such functions? Basically, routing functions, right? So if you get some message, you need to propagate down to your neighbors, right? And then if you have some transactions came on your way, then you can also downstream these transactions to the next set of nodes, right? So that is the routing part, okay? And blockchain database. Basically, these nodes can store the whole blockchain, right? Some nodes only store recent blocks, right? And When they are asked for blockchain, they give what they have to the neighbors, right? So give me your blockchain, then this node will give this blockchain to the other nodes. And then wallet services. We haven't talked about this yet, but we have studied the private key, public key pairs, and then wallet is basically handling these private and public key pairs, and and then using this private key, wallet can be used to send out transactions, right? A wallet, since it has a private key, can use the cryptographic signature algorithm to sign the transaction, right? So that's the main purpose. Private key, public key pair maintenance, and then signing the transactions. And then wallet, other kinds of function wallet could have is what? If there is transactions stored in a block, then should be able to read the block and then make sure that the transaction that you sent has been included in the block. So wallet has these functionalities. And then a wallet is basically an app, right? You can have app developed having these functions: private key, public key pairs, and sending out the transaction, verifying the transaction that you have issued that has been stored in the block, right? And then how many confirmation do you get? One confirmation, two confirmation, three confirmation as time goes on, right? So those are the wallet service. Okay? And so we can just highlight this way. Node can have different kinds of functionality. If a node has every function, right? It has stored the whole blockchain, right? As well as it has wallet. And then it is also doing the mining operation, right? Doing the proof of work, right? And then a node is also doing the routing service to the other, node in the network, right? So such a blockchain, such a node is called a full blockchain. And if a node just doing the routing part, it's just a networking node. And then if there is a node only does the mining operation, right? Then it is a miner machine. And then if there is a node just doing the wallet functionality, then we can call it wallet node, right? So if a node that does this everything, right, then basically I think it is going to be called a full blockchain. Okay, does everything, right? Okay, so node types and roles, you can divide it into these four big functions, right? And that's it for the Bitcoin network part. And then I will move on to the precursors to Bitcoin idea. So there are Bitcoin idea just didn't just came out of thin air, right? There is some precursors to Bitcoin. One of them is these guys. I mean, Hashcash and RPOW, B-Money, Karma, Bitcoin. So as you can see, it goes all the way back to 1998, I guess. Okay, that's that. And then the idea of a Hashcash by Adam Beck, basically proof of work was used to limit email spam. Basically, these days you got, ever since the email has been invented, there are some spam mails, right? So one collect the email addresses from the internet and then send out the advertisement message to all of them, right? Like a million of them. One person can send an email to a million different recipients, as long as the person has gathered the email addresses. Email addresses are usually posted in the internet, and then you can run a crawling algorithm to collect the addresses, and then you can just mass email send out. One can do. So Adam Beck's idea was, let's impose proof of work to the email spammer. So basically, if this email spammer wants to send out the email to each and every one, basically each person has a different address, and then you can create a hash function, right? Having this different email address as an input to the SHA function, right? Then you get different hash output, right? And then you can use the nonce to find some good hash output. Well, you can divide it into two parts, like just like a Bitcoin's POW. Basically, if we do that, then until you get good hash output, you cannot send the email to this person. Okay, so the email spammer need to do some work for each and every person. Okay. If you do that, then basically it is very difficult for the email spammer to send billions of emails to million different people. So that idea was used in 1997, Hashcash work by Adam Beck. And then in 2002, he has used this POW idea to create a token. So it's and then high 0 bit, like what we have studied in this class. Leading 0 bits can be used to create these good and bad hashes, and then he was using it as a token, all right? And then reusable POW by Hal Finney, but he's trying to utilize this POW as a currency. Hal Finney was, but this attempt was a centralized attempt. Basically, he has used a single server to do this. And B-Money by Wei Dai uses POW as a money, and there was a set of servers validating the transactions. But this work has assumed some unjammable broadcasting channel. So, so this is a bit centralized because it requires the broadcast channel, centralized broadcast channel. So that was the downside of this. And another one was karma by this person, and basically I believe I remember that the coin was used to incentivize the computer node who shares their storage element as a file storage. So basically, file is shared among these shared node, and in order for them to provide the computer memory to the network, coin was created and given to them. So it is getting very close to what Bitcoin is doing, right? And BitGold by Nick Szabo, 2005, basically he said that POW is gold. And then but the downside of his work basically was it relied on the IP addresses only. So, but a person can create many different IP addresses, right? So it was vulnerable to cyber attack. Right, and then all right, so that was a couple of, several precursors to Bitcoin, right? And Bitcoin makes use of POW, and then series of blocks chained by hash functions. So that was the original. The original idea was given by this person, Nick Szabo, basically suggested to chain the proof of work, right? So he has done that. Then what was the difference in Bitcoin compared to these previous ideas? Basically, the Satoshi Nakamoto has designed this proof of work system by having the large set of nodes competing for the proof of work race, right? That's what we have seen in our analysis in double spending attack, right? So basically, that was the original idea, right? Given in Bitcoin. POW was not the original idea, but having large set of nodes competing for solving the POW puzzle, and then use this as a mechanism to resolve the conflict among these set of nodes. Basically, the first node who found the solution to the POW wins the race, right? So that's the innovative part, so that large number of nodes can make consensus to determine which block is the best block, okay? Or which block we have to agree on, right? So that was, the agreement is based on the first node who published the block wins, right? That's the, winning idea, basically. All right. So that was the precursors to Bitcoin. Do you have any question for so far? I have covered already 2 items, right? Precursors to Bitcoin. And obviously you can, download these papers and then read more about it. Okay, so I have actually prepared this 2016 article. And then basically, once you read this, you will be able to read more about, behind the stories, precursors to the Bitcoin and so on. This one is very comprehensive survey of technologies around the Bitcoin. And if we take a look at some of them, let's say, Bitcoin protocol it talks about, and the starting point, centralized digital currencies, right? There was previous approaches, like we have just skimmed through it, right? And then proof of work. So basically that was the winning idea used in consensus mechanism. And and then how to prevent double spending problem, it talks about. And how to make use of the SHA-256 hash function in creating POW puzzles, right? And then how the difficulty is adjusted in every 2016 blocks. The blockchain idea, block height, and some of the structures in blockchain, right? Block header and block body, right? And the block body has the transactions, and Buckload hash of the block body is included in the block header. And then these things we have seen already, right, in our lectures. And then double spending attack problem, it talks about it. And script. So this part I am going to cover in the next series of my lectures. And but if you want something to read about it, right, you can take a look at that. So there are lots of reading that you can do, right? Yeah.
Sorry to, I want to know this article's name, title.
It is in the drive.
Yeah, so I found it in drive. I can.
Right here.
Thank you.
Yeah. And yeah, and this is the mechanism how the transaction created by a user or a wallet end up getting into the blockchain. Okay, so it is broadcasted in the peer-to-peer network, and through the Gaship protocol, this transaction is propagated to node around the blockchain, around the whole blockchain network, and then a minor node grab them, put them into a block, attach your POW. When this block is the first, then basically it ends up staying in the blockchain, right? So that's what it is. So you can take a look at them. Comparison with the banking model and Bitcoin. So this is very interesting. Okay. Here there is a very interesting word. So banking model, banking is regulated because they have to keep the balance, right? Somebody make a deposit, they have to keep the balance, right? But Bitcoin, you don't have to do that, right? Because there is a consensus algorithm. It can check the double spending, problem, right? So that's that. And then this is centralized, and then this is distributed consensus. And money creation in bank is done by fractional reserve banking. Right? When somebody make a deposit, let's say $100, then bank needs to keep at least 10% of the deposit money. And then what happens to the 90% of the money? The bank can give out loans out to the people. And the people get this loan, $90 much, and then this person will make a deposit again, right? And then 90% came back to the bank again, and then take the 10% in the reserve, and then rest of the 90% will give out as a loans to the people again. So through this fractional reserve banking, basically tenfold increase in the supply of money. So that type of thing is banking system. But in Bitcoin, there is no such thing, right? Because it's a fixed supply and that's it. Okay. So that was the discussion regarding this one. And then Bitcoin attack vectors. What type of attack could be launched on the Bitcoin network? Double spending attacks, or key. Somebody comes into your handphone and then can steal the private key. So in a wallet, it need to keep the keys in safe place, right? And then basically there should be a technology how to keep your private key in safe place in the handphone or inside your PC, right? So there is a technology, right? Or outright just to remove the private key from the server, right? Once you have this open for login, right? Somebody can break in to the login system and it comes into your system and then take a look at the private key. Then all of money that you have invested in the Bitcoin will be stolen, right? Once private key is given, is stolen, then you don't have control over your fund anymore, right? It is gone, basically. So you have to keep the private key in safe place, and then how can you do that, right? That type of things written right here, okay? And then one other thing is a DDoS attack, okay? If you have a small number of nodes, for example, and then you can send lots of traffic to a single node, then this single node cannot function as a node anymore because it is overwhelmed by the traffic. Then it cannot do communication to the other part of the network, right? And so DDoS attack could be used in double spending attack, launching a double spending attack. For example, there is a link between United States and Korea, for example, through the underwater sea cable, the optical cable. And then there is an entry point in Korea or entry point in California. If you launch an attack, DDoS attack to this node, then basically the two networks will be separated, right? And then after you have done the separation, then you can launch a double spending attack on a partitioned network, okay? So that type of attack is discussed in these papers, okay? And the security, wallet, and cryptography. And then this one talks about elliptic curve cryptography, elliptic curve digital signature algorithm, basically. This is currently used standard set by NIST, but there is quantum computers on the horizon. IBM computer has been preparing launching quantum computers. And then current level of quantum computer is about 300 qubits, right? But when it reaches 1,000 qubits, then elliptic curve cryptography will be broken, okay? And in such a case, then how long does it take for IBM to come up with a quantum computer with more than 1,000 qubits? It is only 1 or 2 years in terms of their planning, right? So we have to be prepared to for this type of technological advances. So let's say one person makes a sphere, new sphere. Previous sphere was just the so let's change the if one person come up with a weapon, right? Let's say advanced missile system, then the other one has to be prepared how to protect themselves from this new missile system, right? So things like that has to go on, in the technological advanced world, right? So we have to get prepared, and then one of the ways that we can be prepared is using post-quantum cryptography, which is having us prepared in the event that quantum computer is introduced. And such research is called post-quantum cryptographic research. And then NIST has been preparing advances in quantum computers, and then they have been doing competitions for 7 years. And then they had 3 rounds. First round, people all over the world who are doing cryptographic research is trying to suggest, post-quantum cryptographic ideas to NIST, and then NIST a subgroup of this submitted idea, and then first round is completed. And then among these selected algorithm proposals, they need to submit another round of ideas to the NIST, and then NIST will select several of them. And then they have done this 3 times. Now 3 algorithms have been selected by NIST, and then those ideas are basically post-quantum cryptographic idea, signature algorithm. One of the algorithms is Falcon, Falcon, and dilithium, and Durandal. So there are 3 algorithms, and that has been selected in the standardization process. And basically, those are the algorithms based on error correction code. But the one that you have downloaded in our Green Bitcoin protocol, the consensus algorithm was what? It was based on error correction code, right? Once you find the code word, you win the race, right? You have solved the problem, right? And then in the post-quantum cryptographic idea, this is actually the same, right? Once you find the code word corresponding to the signature, right? Then basically you have solved the problem, and the code word that you have found is actually the signature, okay? And then we are going to talk about, in the second half of the semester, we are going to talk about zero knowledge proof. And the zero knowledge proof is also based on error correction code, okay? So error correction code is very, very important, okay? But that error correction code idea is not discussed in here, in this paper. But since midterm has been completed, and we can talk about what we are going to discuss in the next half of the semester. So probably, what I'm going to do is this. So we will try to talk about in the next second half Ethereum blockchain. Ethereum is the second largest blockchain in the world. Okay, about 15 times smaller than the Bitcoin network. Okay. And we are going to talk about post-quantum cryptography, maybe a little bit. A little bit. And the other thing is zero knowledge proof. Okay. So this one we will talk about in terms of how to create digital signature algorithm so that we can use in blockchain. This one, right? So what is the characteristic that you need so that you can use in blockchain? First thing is that it should be non-communicative. Once you create a signature, and then you should be able to store this signature in the blockchain, and then anytime, anywhere, take a look at this signature. Should be able to verify if this signature is right signature or not. But there are some cryptography that are communicative, right? I send information to, so I'm the prover and then he is the verifier. Then basically there are communicative signature algorithm. Basically, when when the person try to verify the prover, if the prover has a private key or not, basically the more secure algorithm requires some challenge part. Challenge here means that once there is a proof, then basically this guy challenge again, and then this guy respond and then challenge again, like that. This type of communicative type of cryptography is not suitable for blockchain, right? Because it is not real-time communication, right? Once a person generates a proof, just store in the blockchain anytime in non-interactive way, should be able to verify. Okay? So that's a requirement for blockchain, right? Not in the real time. Real-time cryptography is like this. There is a server, and here is you. You're trying to get into their server system. Then basically there could be an interaction between the two. But we cannot have such kind of situation in blockchain. So that's this part. And the zero knowledge proof is going to be something very new, right? New to most of us, but this was also technology invented in the 80s, in the 80s. So basically, zero knowledge proof is this. There is a prover, again, a verifier, right? Prover and verifier. Basically, prover need to do some work, and verifier is basically giving some job for the prover to do. And then the prover does some work and give that result of the work to the verifier. Right? You can imagine things like this. we have now blockchain, right? Blockchain, you can give money to someone abroad, right? But not through the mechanism of banks and states, right? Without these trusted organization, we are able to give money to anywhere, any person in anywhere where they reside, right? But let's think about, so you can make a payment internationally, person to person, because of Bitcoin innovation, right? So you can give money to anybody around the world. But what do you want to get from this other person? Probably you're not going to give this money just without getting anything, right? So in one hand you give money, and then on the other hand you want to get product delivered, right? And then this that kind of a product is going to be, could be digital product or digital service. So for example, you want to have, let's say, this is you in England, try to give a job to a person in Korea, and then this was a coding job. I want you to program this, right, and give it back to me, right? Then I'll give you money, right? So this, Bitcoin is given to. So basically, result is given to. So coding job is given to this person, and then this person has done the coding, some computation basically, and then return the result. And then this guy wants to get the payment, right? Since this guy has done the work, so this one need to give a Bitcoin to this guy. But in this case, there is a problem, right? What if this